let's talk about the concept of significant figures now. Significant means important, okay, and figure means, in this case it is not 36, 24, 36. In this case, figure means digits, the digits in any measured value, okay. So important digits in any measured value, that is significant figures. In any measurement, in a measurement, all digits that can be directly read from the instrument and one estimated digit are called significant figures. To understand what is significant figure, I have given 3 examples. There are 3 scales: scale 1, scale 2 and scale 3. And what I am doing here is that I am measuring the same length of a pencil using 3 different scales with varying level of precision. This is the least precise scale. This is a lot more precise than this one, and our final scale, that means the 3rd scale, is much more precise than the previous 2. Why this is much more precise than these 2 and why this is more precise than this, we will talk about it. In the first scale, the markings are present at every 6 centimeters. So the first marking is here at 0, the second marking is here at 6, the third marking will be at 12 centimeters, then 18, 24, 30, so on so on. Okay. Now, if I ask you to tell me the length of this pencil using this scale, you will say 4.36 centimeter, right? How? You cannot say anything about the measured value because there is no marking present in between 0 and 6. Okay, so you cannot tell me the exact value. You cannot tell me the length of this pencil, right? Now, see this statement. In a measurement, all digits that can be directly read from the instrument. Now there is a simple rule to write any measured value. First, write all digits that can be directly read from the instrument. Is there any digit that you can directly read from this instrument? No. You cannot read any digit in this instrument because there is no marking between 0 and 6. So this part is of no use for us in this case. Now, after writing all the digits that can be directly read from the instrument, in this case we cannot directly read any digit. So finally add one estimated digit. Now we will use our ability of estimation. Okay. So I will write it the length. I can write the length as even 1 centimeter. I can report it because it completely depends upon my estimation, upon my ability to make estimations. Okay. So I can report this length as 1 centimeter, 2 centimeter, 3, 4, 5. I can report it because it completely depends upon my ability of estimation. Clear? Remember, you can only write 1 digit using your estimation in any reported value, not more than that. So the very first digit I will report for the length of this pencil would also be the last digit of my measurement. So I cannot write 2 point something or 3 point something, because that would be a case where I am using more than 1 digit. Okay, so I can write only 1 digit to report the length of this pencil. I can either write 1, 2, 3, 4 or 5. So let me estimate now. It completely depends upon my ability of estimation. 3 should be somewhere here, 4 should be somewhere here, I think so. So this value should be, I think, let's say 3 is somewhere here, 4 is somewhere here. So it should be 3.3. I cannot write. I know that I can guess that it should be 3.3 something, right? But I cannot write the next digit. I can only write 1 digit using my estimation. So this is the end. This is my reported value, 3 centimeter. Okay, now let's move on to the next scale and read this statement again. Significant figures. In a measurement, all digits that can be directly read from the instrument and 1 estimated digit. Here, this scale is clearly telling me that the length is lying somewhere between 3 centimeter and 4 centimeter. So it must be 3 point something. 3 is the digit I can directly read from the instrument, 3. And 3 point something, 3 point what? I cannot read. So now I will use my ability of estimation. Okay. I will mentally divide what I will do. I will mentally divide this distance into 10 equal parts. Okay. So according to me it should be 1, 2, 3, 4, 5. It should be somewhere 3.3 centimeter. I will report my measured value as 3.3 centimeter. The first value is the digit I directly read from the instrument, and the second value is coming from my estimation. I have to stop here. I cannot just keep estimating forever 3.321056. No, I cannot do that. I can only use one extra digit using my estimation in my measured value. Okay. Now let's move on to the third scale. Here, this scale is clearly telling me that the measured value is the length of this pencil is lying somewhere between 3.2 and 3.3. So it should be 3.2 something. This scale is not telling me anything about the third digit. So this digit will come from my estimation. The first two digits are I can directly read from the instrument, from this scale. Okay. First, write all digits that can be directly read from the instrument. So 3.2 I can directly read from the instrument, so I wrote it here. Then the final digit will come from my estimation, and 3.2, 3.3, if I mentally divide this portion into 10 equal parts, I think it should be somewhere between 3.28. I could have estimated it as 3.27, 3.29, even 3.24, 3.25. 3.2 cannot change because this is something the scale is clearly showing me. The third digit that is coming from my estimation may change because it completely depends upon my estimation. So now our first scale is least precise. Our second scale is much more precise than this one, and our third scale is even more precise than the previous two. Why it is least precise? See, in this case, the physical quantity being measured is length, and the true value is this much. Okay, so I can report this length as 1 centimeter or 2 centimeter or 3 centimeter. If I repeatedly measure this length, I can, since the very first digit is coming from my estimation and I have to stop here. Okay, so I can report it anything between 1 and 5 centimeter. See, the possible results are quite far from each other. That is why this scale is least precise. Okay, in this case, the possible result of my measurement must lie between 3 and 4. This scale is clearly telling us. So this is much more precise. And in this case, the possible result of my reported measured value must lie between 3.2 and 3.3. This scale is clearly telling me that the length is lying somewhere between 3.2 and 3.3. Since here the possible measured values are very close to each other, this scale is much more precise. Here the number of significant figure is 1, here the number of significant figure is 2, and here the number of significant figure is 3. Why here number of significant figure is 1, here 2, and here 3? We will talk about it very soon. Here, if I report this length to someone, by just looking into my reported figure, he would be able to say that I have used a scale much more precise than this one to measure this length. And if I, instead of this, I report a length of 3.28 to someone, he would be able to tell that I must have used some scale much more precise than the previous two scales. The number of significant figure in any measured value clearly tells the level of precision in that measurement. Okay, the more is the number of significant figure, the greater is the level of precision. The less is the number of significant figure, the lesser is the level of precision. See, while doing calculations involving measured values, okay, that means multiplication, division, subtraction, addition, etc., involving measured values, the concept of significant figures help us a lot to predict to which digit we have to round off. We have to do rounding. Okay, you will know it later, don't worry. Now let's learn the rules to find the number of sig figs. There are 7 to 8 rules. Let's study them one by one. The first rule says all non-zero digits are significant. Of course, we are talking about measured values, a number that we have obtained from measuring some quantity, some physical quantity. Okay, the first rule says in any measured value, all non-zero digits are significant. That means, say my measured number is 2.345. Okay, so here the number of sig figs is 4. Significant figures. Sig figs means significant figures. 356.56. The number of sig figs 5. Why? Because there are 5 non-zero digits, and all non-zero digits in a reported value, in a measured value, are significant always. Okay, 3576 or 7892.32. This value has, this number has 1 2 3 4 5 6 6 significant figures, and this number has 4 significant figures. Okay, of course we are, all these numbers are measured values. Clear? Let's see the second rule. All the leading zeros are insignificant. Leading zeros are those zeros which comes before the first non-zero digit. 0.03456. This has 4 sigfix. Why? 4 sigfix. These two zeros are leading zeros, means zeros coming before the first non-zero number. The first non-zero digit here is 3, and these two zeros are coming before it, so they are not significant or they are insignificant. So there is always only 4 significant fix in this number. Let's consider 0.000567. This has 3 sigfix. 1 2 3. All these zeros are leading zeros. They are coming before the first non-zero digit. In this case, the first non-zero digit is 5, and all the zeros coming before it are leading zeros, and they are always insignificant. So in this number, only 3 significant figures are present. Okay. 0.5. Here the number of sigfix is 1. This is the only significant figure here because this 0 is the leading zero coming before the first non-zero digit. Clear? Let's move on to the third rule. All zeros lying between any two significant figures are also significant. That means trapped zeros are always significant. Trapped zeros, that means all those zeros which are lying between any two significant figures are also significant. For example, 3056. This 0 is lying between significant figures. You can say this 0 is lying between 3 and 5 or 3 and 6. Okay, so this 0 is also significant. All zeros lying between any two significant figure are also significant. So this number has 4 sigfix. 3056 has 4 sigfix. 300.56. This number 300.56 has 1 2 3 4 5 sigfix. Why? This is significant, this is significant, this is significant, all being non-zero numbers, and these two are lying between significant numbers, so these two are also significant. These two are trapped zeros. These two are trapped zeros. They are lying between significant numbers. So the number of sigfix in this case is 5. Let's consider another example. 0.03567. In this case, the number of sigfig is, this 0 is significant? No, it is leading 0 coming before the first non-zero digit. These two zeros are leading zeros, so they are not significant. Now, this is significant, these two are not significant, this is significant, this is significant, this is significant, this is significant. And this 0 is lying between significant figures, So this 0 is also significant. So in this case, the number of sigfig is 5. The number of significant figure is 5. Rule number 4 says trailing zeros are significant if they appear after the decimal. What does trailing zeros mean? Trailing zeros means all those zeros which are lying after the last non-zero digit in any measured value. Okay. So in 300, the number of sigfig is 1. Why? 3 being a non-zero digit is a significant figure, but these two zeros are significant or not? They are not significant. Why? Because although they are trailing zeros, but they are not appearing after the decimal. There is no decimal in this number. So there is only one sigfig in this case. Let's talk about, this is our first example. Let's talk about 300.00. What do you think? What is the number of sigfig in this case? The number of sigfig is 1 2 3 4 5 5. Why? 3 being a non-zero digit is significant. These two zeros are significant because they are trailing zeros and they are appearing after the decimal. These two are also trailing zeros, but they are not appearing after the decimal. Only these two zeros are appearing after the decimal. So we know now that these 3 are sigfix. These two are also sigfix. Why? these two will automatically become sig figs because they are lying between sig figs, right? All zeros lying between any two sig fig are also significant. Okay, so these two zeros, since they are lying between significant figures, so they are also significant. So the number of significant figure in this case is 5. Now let's take another example. 0.0003050 0.0003050. Not significant, not significant, not significant, not significant. All are leading zeros, and leading zeros are never significant. 3 is significant, 5 is significant. This 0 is also significant because it is trailing zeros appearing after. Trailing zeros means appearing after the last non-zero digit. Here the last non-zero digit is 5. So this 0 is trailing 0 and it is appearing after the decimal also. So this will count as a significant figure. Now what about this 0? Of course, obviously this 0 will also be a significant figure because it is, there are significant figures in both of its sides, right? It is lying, this 0 is lying between significant figures, between 3 and 5. So this 0 as well is significant. The number of significant figures in this case is 1, 2, 3, 4, 4. 3, 0, 5 and 0. There are 4 sig figs in this case. Let's talk about 0.0500. Let's talk about 30.0500. Okay, so this 3 being a non-zero digit is significant, 5 being a non-zero digit is significant. These two zeros are trailing zeros and appearing after the decimal, so these two are also significant. Obviously these two digits are also significant. Why? From rule 3. They are lying, these two zeros are lying between significant figures 3 and 5. So in this number we have a total of 1, 2, 3, 4, 5, 6 sig figs. Total 6 significant figures are present in this number. Clear? Let's take few more examples. Let's take few more examples. 67600.050. How many sig figs are present in this number? 6, 7 and 6 are sig figs. This 5 is also sig fig because all these digits are non-zero. Now this 0 being trailing 0 as well as lying after the decimal is significant. Okay, now all these zeros will automatically become significant because all these are trapped zeros. They are lying between significant figures. That means there are significant figures in both the sides of these zeros. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, a total of 8 sig fig in this case, 8. Okay, let's talk about 3050.0500500. And let's take another example, 0.003050000. In this case, the number of sig figs, all these 3 are leading zeros, so they are not significant. These 4 are trailing zeros and appearing after the decimal, so these 4 are significant figures. This is significant, this is also significant, and this 0 will also be significant because it is lying between two significant figures. Any 0 lying between two significant figures is also significant. We call these zeros as trapped zeros. Okay, so the number of sig fig in this case is 1, 2, 3, 4, 5, 6, 7. Let's consider this example. 3, 5, 5, 5. All these are sig figs. These two being trailing zeros, that means zeros appearing after the last non-zero digit and also after the decimal. So these two are significant figures. Now the remaining zeros, this is a trapped zero. In both of its sides there are significant figures 3 and 5. These two zeros are also trapped zeros. There are significant figures in both their sides, right? These two as well as sig figs because these two are also trapped zeros. So all the digits are significant in this case. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 sig fig. Clear? So this is how we find the number of significant figures. Still there are 3 more rules. Constants which are a part of a formula has infinite sig figs. थोड़ा सा erase हो गया, don't worry. Constants which are a part of a formula has infinite sig figs. That means, see, these rules are applicable for measured values. If there is a constant which is not measured, it is just a part of a formula, then there is infinite significant figure in it, right? For example, let me give you example. Kinetic energy, half mv square. This too is not a measured value, right? This too is a part of the formula. So we will say that there are infinite number of significant figures in this too, in this number. And it is obvious also. Why? You can write this 2 as 2.00000000, so on, so on. There are infinite number of significant figure in this 2 because we know it is exactly 2. It is not a measured value. It is a number, exactly 2. It's a part of the formula. Since we know it with so much perfection, so we can say that there are infinite number of significant figure in this digit. Okay. You can put any number of zeros after it, after putting a decimal. Okay. Similarly, let's say radius is half the diameter. In any circle, radius is half the diameter. So this too also has infinite number of significant figure because it is not a measured value. It is a part of the formula and we know that it is exactly 2. So this 2 can be written as 2.00000000, so on, so on. It has infinite number of significant figures, right? Similarly, any constant which is a part of a formula has infinite number of significant figure. Pi, the circumference of a circle is 2 pi r. So here this 2 and pi both has infinite number of significant figures because we know the value of pi exactly. It is not a measured quantity, as well as 2. 2 is also not a measured quantity. It's a constant. We know it is exactly 2. We have not measured it using some instrument. Okay. So these two has infinite number of significant. Moving on to the next rule. When a measured value is represented in scientific notation that we also call standard form, the number of significant figures in it is equals to the number of sig fig in the mantissa. See, any measured value can be represented in the form of a into 10 raised to the power b, where there is a condition a should be greater than equals to 1 but less than 10. When a number is represented in this form, provided a is greater than equals to 1 but less than 10, we call it standard form. Okay. If you want to find the number of significant figure in any measured value represented in standard form, then what you have to do is just ignore 10 raised to the power something part and focus here. A, the number of significant figure in A is equals to the number of significant figure in your measured value. Like 2.3 into 10 raised to the power 3 has 2 sig fig. Ignoring 10 raised to the power something part, A, here A is 2.3, so number of sig fig is 2. 1, 2. 2.30 into 10 raised to the power minus 3. Here the number of sig fig is 3, ignoring 10 raised to the power something part. Focus here. Here A is 2.30 and number of sig fig is 3. Non-zero digit, both will be significant figure, and this being trailing 0 and after decimal. So the number of sig fig here is 3. Clear? Just ignore 10 raised to the power something part or focus on the value of A only. The number of sig fig in A would be equals to the number of significant figure in your measured value. Okay. Now, unit converter does not change the number of sig fig. See, suppose I have a value 2.3 kilometers, right? Or 1 meter. 1 meter is equals to 100 centimeter. In 1 meter, the number of sig fig is 1. In 100 centimeter, again, the number of sig fig is 1. When you are just converting unit from meter to kilometer or from kilometer to miles or anything, okay, you cannot become more accurate, right? You cannot become more precise. So while converting the unit, always keep it in your mind that the number of significant figures should not change. Because by just converting the unit, you cannot become more accurate and precise. The level of precision is same, whether you are reporting a value in kilometer or meter or centimeter or millimeter or any other unit. So the number of significant figure should never change while converting units. Clear? So here 1 meter is written as 100 centimeter. The number of sig fig is same. 2.3 kilometers is 2300 meters. The number of sig fig is same, right? Now 2.30 kilometer cannot be reported as 2300 meter. Mathematically it is true. 2.30 kilometer is also 2300 meter. Mathematically it is true, but from the perspective of significant figure, it's false. How? Here the number of significant figure is 3. 2 and 3 both are significant figure, and 0 as well is a significant figure because it is lying after the decimal and it's a trailing 0. Clear? But here the number of sig fig is only 2, right? So mathematically it is true, but from the point of view of significant figure, it's wrong. So instead of writing it as 2300 kilometer, we would write it as in the standard form. We would now write it in the standard form to make the number of significant figure 2 even after the conversion of unit. Okay, so I can write it as 2.30 into 10 raised to the power 3 meter, right? Now 2.30 mathematically this and this, all of them are equal, but from the point of view of significant figure, this is equals to this, not this. 2.30 kilometer is not equals to 2300 meter because number of sig fig is here 3 and here 2. That means this value is more precise than this value, and it cannot happen because you are just converting the unit from kilometer to meter. But here, see, in this case 2.30 kilometer, when I represented it in standard form or scientific form, now 2.30 into 10 raised to the power 3, this has 3 sig fig, here 2, the number of sig fig was 3. So this is the correct way of writing it. Now if this measurement instead of 2.30 kilometer, you wish to convert 2.300 kilometer into meters, here number of sig fig is 4. So ensure that even after conversion of unit, the number of significant figure does not change. So we will write it as 2.300 into 10 raised to the power 3 meter. Here we won't write it as 2300 meter because here the number of sig fig is 2 and here the number of sig fig is 4. Mathematically it's true, but from the point of view of significant figure, it's false. This is the correct way of writing your measurement in your measurement. Always ensure that while converting the unit, the number of significant figure is not changing. Here number of sig fig was 4, here too the number of sig fig is 4 because we are just representing our measurement in standard form in a way to ensure that this number 2 has number of sig fig 4. So we wrote it as 2.300 kilometer to make the number of significant figure 4. That's it.